Alright, welcome back. So, let's start. So the last time we interpreted homogeneous polynomials as holomorphic sections of holomorphic line bundles, right? So homogeneous polynomials were used to produce examples of submanifolds of CPN, that's projective varieties. And we wondered if these homogeneous polynomials could be thought of as functions from CPN to somewhere. Indeed, they're functions. They're much more than functions. They're holomorphic sections of certain holomorphic line bundles, the OK bundles. OK is simply O1 tensor product with itself k times. And O1 is the dual of the tautological line bundle. The tautological line bundle has a very simple description. Well, what is CPN? Simply the collection of lines through the origin. So to every line, associate the one-dimensional vector space represented by that line. Yeah. Then we defined almost complex structures, simply endomorphisms of the tangent bundle such that j square is minus I. Compatible Riemannian metrics, that simply means j preserves the Riemannian metric. And if you have a compatible Riemannian metric, you can define a form, a 2 form. Omega of x comma y is g of jx comma y. This form turns out to be a 1-1 form when you look at the tangent bundle as a complex bundle with the almost complex structure J. Please recall that the real tangent bundle with the almost complex structure defines a complex vector bundle. The holomorphic tangent bundle with its usual complex structure also defines a complex vector bundle, and these two are isomorphic. So we can freely pass from one to the other. Alright, and we looked at the expression of the volume form of a compatible Riemannian metric. It was omega raised to n over n factorial. Yeah. Alright, so let's move on. So what are examples of compatible Riemannian metrics on complex manifolds? What's our simplest example of a complex manifold? Well, it's simply an open subset of Cn. What's an obvious example of a metric there? It's the usual Euclidean metric. Now that metric is compatible with the usual complex structure. I mean, it's the same reasoning as to why the usual almost complex structure of R2 is compatible with its metric, because the usual almost complex structure is simply rotation by 90 degrees, right? The same kind of reasoning here too. Right? So the Euclidean metric, its associated 1-1 form is simply dz1 wedge dz square root of minus 1 over 2 times dz1 wedge dz1 bar plus dz2 wedge dz2 bar plus so on. It can be concisely written as square root of minus 1 over 2 del bar mod z squared. Okay. Alright, so the usual Euclidean metric on Cn functions as an example. Now the Euclidean metric on Cn descends to a metric on complex tori, because complex tori are quotients of Cn by means of translations, and translations preserve the Euclidean metric. Yeah? So now we have a compact example of a compatible Riemannian metric. So if you want to come up with more examples in Cn, well, one obvious way to do it is to simply take any Hermitian metric, right? That's going to give, its real part is going to be a compatible Riemannian metric. But how do you come up with examples of Hermitian metrics? Is there a systematic way of doing that? In fact, for that matter, even in Rn, how do you come up with examples of Riemannian metrics? Of course, a Riemannian metric is simply a positive definite matrix valued function, right? But how many such functions do you know other than the constant one, or things constructed out of the constant one by means of a partition unity or something, right? Is there a systematic way to do it even in Rn? Forget about Cn. There is a way. So for instance, in Rn, If you take a convex function, a strictly convex function, then its Hessian, the second derivative matrix, is positive definite, right? So that can be an example of a Riemannian metric, Hessians of convex functions. Akin to that, if you take a smooth real valued function in Cn such that d square phi dzi dz bar j, this is going to be a complex matrix, right? Sorry, there's a typo there. All I wanted to say is hij bar is ji bar, the whole thing bar. Namely, this is a Hermitian matrix, right? For those functions phi for which it is positive definite, we can get an example of a compatible Riemannian metric by using this Hermitian matrix real part, right? So this is a very systematic way to produce examples in Cn. I believe this construction is due to Kayla, but I haven't verified the historic authenticity of this remark. Nonetheless, any smooth function satisfying this property that its complex Hessian is a positive definite matrix, such a smooth function is called plurisubharmonic. Okay. Why is it called plurisubharmonic? What does it have to do with harmonic functions? Well, if I take the trace of this matrix hij bar, that's its d square phi dz1 dz1 bar plus d square phi dz2 dz2 bar plus so on, that is going to be the Laplacian of phi up to a factor, right? So the fact that hij bar is positive definite means that its trace is a positive number, which means the Laplacian of phi is positive, which means it's subharmonic. Yeah. Unfortunately, not all Hermitian metrics in Cn arise this way. That is, you can't always find a function phi. That's not so shocking, right? If the ability to find such a function phi is the ability to solve a system of partial differential equations, and that too with just one unknown, right? If you are giving me all components of hij bar and you just want one single function such that hij bar is its second derivative. So that is highly overdetermined, right? So it's no shock that not all metrics are of this form. More concretely, if H is of this form, there's a very interesting observation here. If H is of that form, then the induced form, what is the induced form? Recall, it's simply the imaginary part of H, up to a factor, of course. This induced form, I mean, if you want to write it down explicitly, it's hij bar dzi wedge dzj bar sum over ing times square root of -1 divided by 2, or you can omit the 2, whatever, right? Now it's not at all hard to calculate the d, the exterior derivative of this induced form, and this exterior derivative is closed. Now this exterior derivative of omega, d omega, is 0, right? So if H is of that form, then d omega is 0, and hence, since omega is a 1-1 form, del omega is 0, del bar omega is also 0. So this is a necessary condition, yeah? Is it sufficient is the next question. If d omega is 0, at least locally can you find a phi that works? You can. It's not trivial though. First of all, remember the Poincare lemma in usual differential geometry, namely closed forms on balls are exact. There's a version of that for the del bar operator, namely del bar closed forms on a ball are del bar exact. It's not trivial to prove, by the way. It's not as straightforward as in the real context. Nonetheless, even given this lemma, it's not clear, but a little bit of work shows that for every closed real 1-1 form omega, what do I mean by real form? That means omega equals omega bar, right? For every closed 1-1 form omega on a ball, you can always find a phi so that omega is square root of -1 del bar phi, where phi is real valued. Okay, So this gives a converse of the previous thing, meaning if Hij bar is a metric on a ball in Cn, Hermitian metric, whose associated 1-1 form omega is closed, then Hij bar must arise due to this construction of Kayla. That is, there is a function phi so that Hij bar is d square phi dzi dzj bar. Okay. By the way, this lemma is given a name. It's called the del bar lemma. Okay. All right. So, motivated by this phenomenon, let's look at what happens on manifolds. A complex manifold with a Riemannian metric is said to be a Kayla manifold, and G is said to be a Kayla metric if, firstly, G is compatible with a complex structure. This is almost an obvious requirement, and the associated 1-1 form omega is closed. So a Kayla metric is such that omega is closed, so omega is locally del bar of some function. Yeah. By the way, it is very common in complex geometry to refer to omega itself as the Kayla metric. Obviously, omega is not a metric; it's a two-form, right? But you can easily recover the Hermitian metric and hence the Riemannian metric very easily from omega. How you write omega in local coordinates? It will be square root of -1/2 Hij bar dzi wedge dzj bar. That Hij bar is the Hermitian metric, right? So, how do you recover the Riemannian metric? You take Hij bar dzi tensor dzj bar and take the real part of it. You'll recover the Riemannian metric. Okay. So from now on, whenever I say let omega be a Kayla metric, what I really mean is omega is the 1-1 form associated to a Kayla metric. Okay. The first step here is not every complex manifold admits a Kayla metric. So rather unfortunate. It seems like a very natural way to get metrics, but not every complex manifold admits a Kayla metric. Okay. By the way, while it may seem very natural, this notion of Kayla, because I told you what it looks like in Cn, there is a deeper reason to study Kayla geometry. We'll see that soon. Okay? The notion of Kaylaness is forced upon us. It's not something that one just comes up because of pure luck. Okay? So not every manifold admits a Kayla metric. What's a counterexample? The Hopf surface is a classic counterexample. Why is it a counterexample? I'll come to it in a moment. Okay. Now, here is the really interesting question. If you remember your Riemannian geometry, for every Riemannian metric, if you give me any point, there is a neighborhood of that point such that there are normal coordinates for G. What does that mean? That means there's a coordinate system such that up to the first order, G agrees with the Euclidean metric. Right? So G is simply the Euclidean, G at that point is the Euclidean metric. Its derivatives at that point, its derivative at that point is 0. The first derivative. The second derivative onwards, we have no control. Right? So a natural question in a complex manifold is, if you give me a Riemannian complex manifold with G being compatible with a complex structure, can you always find holomorphic coordinates such that G is standard up to the first order? Right? Now that's not obvious. In fact, if you can find such holomorphic coordinates, then omega is also standard up to the first order, obviously. So that means the derivatives of omega, in particular the exterior derivative of omega, in these coordinates is 0. So if it's 0 in one coordinate system, at that point it's 0 in all coordinate systems. So that means the ability to find holomorphic local coordinates has a necessary condition, namely that omega is Kayla. And it turns out it's also sufficient. Okay, and the proof is not very hard, so I'll give you a sketch here. So firstly, choose your favorite holomorphic coordinate system Z tilde, such that at least at the point P, omega is Euclidean. Well, how can you do that? Take any coordinate system and use a linear map to diagonalize the metric at that point. Okay, so there is an obvious coordinate system Z tilde, so that omega is standard up to the 0th order near that point. Now we'll change our coordinate system. We'll say Z equals Z tilde plus a quadratic term. Such a transformation is not always invertible. However, if Z tilde is small enough, the quadratic term is heavily dominated by the first order term. Therefore, this transformation is a biholomorphism for small enough Z tilde. How small Z tilde has to be depends on B, obviously, right? The point is, you can always choose a B appropriately so that these become normal coordinates. Well, how exactly? If you look at what the metric looks like in a new coordinate system, well, it involves the derivative of the change of coordinates, right? The derivative of this particular change of coordinates is the identity matrix plus B times Z tilde, roughly speaking, right? So if you substitute this in the change of coordinates formula, you can choose a B so that the first order term gets cancelled out. But if you just do this calculation, you'll see that you need some sort of a symmetry in the first order term to make sure that you can find a B that cancels it out. That symmetry is precisely the Kayla condition. Okay, please do it as an exercise so you'll see why you need the Kayla condition. Okay? Alright. Okay, so notice that the Kayla form, for a Kayla manifold, the form omega is closed, right? Natural question is every closed form exact? Of course, since I'm assuming that you know differential geometry, I hope you know what de Rham cohomology is. The de Rham cohomology consists of closed forms quotiented out by exact ones. Not every closed form is exact. However, if you take a compact manifold, if you take any closed form, it up to some finite dimensional space, it's exact. Meaning if you subtract out a finite dimensional quantity from it, it becomes exact, right? So the de Rham cohomology is closed forms quotiented out by exact forms. Likewise, you can form the Dolbeau cohomology groups, namely you take PQ forms that are del bar closed, and you can ask which ones are del bar exact. This cohomology group measures the obstruction for this. In other words, it's del bar closed PQ forms quotiented out by del bar exact ones. Okay. For Kayla manifolds, turns out, and this is because of some fancy PDE, this is the Hodge theorem. In hindsight, although I said that I don't really require any prerequisites of PDE to understand my lectures, while that may be true on paper if you're willing to take certain things on faith, in practice, you know, I mean, I really don't know if I'll ever get to the proof of the Calabi conjecture, but if I do get to that, the Calabi conjecture is a PDE, so of course you would need to know some PDE theory to understand it. But anyway, so it turns out for Kayla manifolds, these Dolbeau and de Rham cohomology groups are very strongly related to each other. A priori, it's not clear that they should be related, right? But it turns out, if you know all the Dolbeau cohomology groups, you can compute the de Rham cohomology groups. Because HK is simply the direct sum of HPQ, where P plus Q equals K. This relation seems natural enough, but it's not true in general unless your manifold is Kayla. Notice this interesting phenomenon. fact that a manifold is scalar simply means it admits some scalar metric. But this particular equality of cohomology groups has nothing to do with metrics at all, right? So if you have a nice Riemannian metric, you have some conclusion involving topology or complex geometry, right? Already. Alright, so just like the local del power lemma, there's a global del power lemma, and it's extremely important for our purposes. It says the following: if omega is a D-closed 1-1 form, then it is D-exact if and only if it's del bar exact. Meaning if omega is d eta, where eta is some one form, then actually omega is del bar of some function f, right? In particular, moreover, if omega is a real d-closed 1-1 form and it's d exact, then omega is square root of minus 1 del bar phi, where phi is a real valued function. Yeah, so this is just the analog of the usual del bar lemma, the local one. The only condition imposed here is omega better be d exact as well. In the local case, that follows for free because of Poincare lemma. Yeah? If omega is a Kayla form, it defines a de Rham cohomology class. Why? Because if omega is Kayla, that means d omega is 0. So you can of course take the equivalence class under the de Rham equivalence relation. So this is a very interesting observation. This de Rham cohomology class is never 0. What does it mean for it to be 0? If it is 0, omega is exact. Omega can never be exact on a compact manifold. Why? If it's a Kayla form, it can never be exact, because if it is exact, what is omega raised to n? Omega raised to n is also exact. Closed form, wedge, and exact form is exact. But if you take an exact form and you integrate it over the manifold, by Stokes' theorem, you'll get 0. It has no boundary. However, omega raised to n over n factorial cannot have 0 integral because it's a volume form. So in other words, if your manifold does admit a Kayla metric, its second cohomology better be non-trivial. In fact, that is how you can prove that the Hopf surface cannot admit a Kayla metric, because you can easily compute its second cohomology. It's diffeomorphic to S1 cross S3. If you know some algebraic topology, you can use the Q-net formula and compute the second cohomology, and that'll be trivial. Okay. Another very important observation is, if you take any other Kayla form in this cohomology class, let's call it omega prime for instance, then omega prime minus omega is d exact, it's d closed, it's a real 1-1 form. So the global del bar lemma says that omega prime is omega plus square root of minus 1 del bar phi for some smooth real value function phi. So every Kayla form in this Kayla class is given by omega plus square root of minus 1 del bar phi. Okay, alright. So what's mathematics without examples, as Claude Lebrun would say? So what are examples of Kayla manifolds? Well, whatever examples you can find, all the submanifolds will be Kayla. Why? Because if you take a metric and you take the induced metric, well, the associated form is simply the restriction of this form. So if the original one is closed, this is also closed. Okay. The complex torus with the Euclidean metric is an obvious example of a Kayla metric. Right? What about the Hopf surface? That does not have any Kayla metrics, as we just proved. What about CPN? Not only does CPN have a Kayla metric, there's a very nice Kayla metric called the Fibonacci metric on it. If I show you the formula, it won't be clear as to why I'm calling it nice, because it's horrible to look at, right? So we'll take our favorite coordinate chart. X0 is non-zero, so you take x1 over x0 as z1, x2 over x0 as z2, etc. The Fibonacci matrix formula, and I'm going to write the formula of the associated 1, 1 form. Okay, as always. Square root of minus 1 del bar of log of something. Now, I mean, this is not good enough to define the Fibonacci metric because I have to tell you what it looks like in the other coordinate charts and I have to make sure that it's the same beast. I'm not going to do that. I'll leave it as an exercise for you to figure out what it will look like on the other coordinate charts and why it will agree with this. Okay. But in this chart, it's locally del bar exact. Hence it is declosed. Hence it is an honest Kayla. It's at least, there's a chance that it's a Kayla metric. But we have to compute it and see that the matrix is positive definite. Right? That's not obvious. If you just write down del bar phi, where phi is any old function, you're not going to get a metric out of it. Right? But I'll leave that also to you as an exercise. But if you look at this expression, it's not clear as to how you could have come up with it, but we'll come to that question later on. Okay, so please do these calculations and check that indeed this is an honest Kayla metric. So as a consequence of this point and the first point, any smooth submanifold of any complex submanifold of CPN is a Kayla manifold. Okay. Of course, if you take any randomly chosen torus, it's Kayla, but it's not projective as I told you earlier. So being Kayla does not mean you're automatically projective. Okay. But it's a necessary condition. If you are a projective variety, you better have a Kayla metric. Heck, the Fibonacci metric does the job. Okay. Alright, let's go to this question. So this Fibonacci metric has a very strange formula. If you didn't already know the formula, how could you have come up with it on your own? There are, by the way, many ways to do this. One way is the following. CPN can be interpreted purely from the perspective of real differential geometry without knowing what a complex manifold is. CPN is diffeomorphic to S2n plus 1 quotiented out by S1. Okay, so it's a quotient of a sphere. The sphere already has a metric, a very nice metric. Turns out that metric survives when you do the quotient operation and it gives you a metric on a Riemannian metric on CPN. That Riemannian metric up to a factor is simply the Fibonacci metric. But that also, I mean, if I didn't tell you that little thing, you wouldn't have come up with it, right? So is there a systematic way of coming up with Kayla metrics, right? So there is. I'll tell you, I mean, the answer, you may not know what it means yet. You'll know by the end of this lecture. Indeed, there is a systematic way. You take a metric on an appropriately chosen line bundle, in this case the O1 bundle, and compute its curvature, the curvature of some connection associated to this metric. That turns out to be the Fibonacci metric, or more generally, that might be a Kayla metric. Okay. All right. So some generalities about holomorphic vector bundles and connections. Alright, I'm assuming that everyone knows what a connection is and what curvature is for vector bundles. If you don't, and if you know what the Levi-Civita connection is on the tangent bundle, it is somewhat similar to that notion. Basically, what's a connection? It's a way of computing directional derivatives of sections along certain directions, right? So that's the rough concept, but please brush up about connections. Okay. All right. So if you have a holomorphic vector bundle over a complex manifold, and suppose you have a Hermitian metric on it, there exists a unique connection, there exists a unique way to take directional derivatives that satisfies a couple of properties. That's metric compatible, meaning just like for the Levi-Civita connection, if you take S and T is inner product, the D of that is nabla S inner product T plus S nabla T. Right? So that's a fairly natural requirement. The second requirement is not so obvious. It's compatible with the complex structure. What does this mean? What this means is the following. So suppose you take a holomorphic trivialization. Right? So if you take a holomorphic trivialization, every section of this bundle, suppose a trivialization consists of, what's a trivialization? A trivialization is a linearly independent choice of sections, meaning it's a holomorphically varying basis, basically, right? So if you take this holomorphically varying basis, let's say it's EI of Z, every section S is a linear combination of these EI, so it's sum over SI, SI, EI, right? So what is a connection acting on a section? Well, so a section can be locally identified with a vector full of functions. All the SIs are functions. So locally, a connection acts on a section to give you a vector full of 1 forms. Okay? Right. Now the 0, 1 part of these 1 forms will be something. If that something is simply the del bar operator acting on these functions, then the connection is said to be compatible with the complex structure. I know it's a lot of words to take in, and had this been a face-to-face lecture, I would have written this down in greater detail, but please look it up. I mean, I hope I've made myself clear, but nonetheless, what we really care about right now is not that. You can take it on faith that here is the formula for such a beast. So suppose you take a holomorphic trivialization, the connection is of the form D plus A. Any connection in any trivialization is of the form D plus A, where A is a matrix of 1 forms. Okay. This is a general fact about connections. There's nothing so specific about holomorphic vector bundles or anything here. Okay. But in a holomorphic trivialization, this particular connection has this formula. What you do is you take H, the metric H in any holomorphic trivialization is simply represented by a Hermitian matrix H. Take del of this Hermitian, del of H bar. What that means is if you take the matrix, for each component take del of that component, then multiply it on the left with H bar inverse. So this gives you a matrix of 1 forms. In fact, it gives you a matrix of 1, 0 forms. I claim that these matrices define a connection. Okay. This connection is called the Chern connection, because Chern came up with it first. Alright. Now I assume you know what curvature means. If you don't, you have to read it up. Curvature basically, so yeah, I mean it'll take me too far afield to define what curvature is, but as far as you're concerned, if this is the first time you're seeing these things, A is locally a matrix of 1 form, so take dA plus A wedge A, it's locally a matrix of 2 forms, right? That local matrix is called the curvature. Right. Alright, and that particular matrix in our situation can be simplified, this expression, to the curvature matrix being del bar of H bar inverse del H bar. Okay. So why do I care about these things? Notice for a line bundle, the curvature is simply dA, because A wedge A is 0, A is a 1 cross 1 matrix of 1 forms, and any 1 form wedge itself is 0. So theta is simply dA, yeah, for a line bundle. Now theta is a collection of locally defined matrices of forms, right? And in this case, in the case of a line bundle, is just locally it's a 2 form. But it turns out that all these local 2 forms agree with one another on the overlaps, and it becomes a global 2 form for a line bundle. Okay. All right. So for a line bundle, once again, what is the expression for the curvature? It's del bar A. What is A? It's h bar inverse del h bar. H for a line bundle is simply a positive function locally, right? What's a Hermitian 1 cross 1 matrix? It's simply a positive number, right? So h bar inverse del h bar is simply del log h, right? So theta is del bar del log h. And as I said earlier, this theta, although I'm defining it locally for a line bundle, it's a globally defined smooth form. So an interesting question is, what does it look like if you change your metric on the line bundle? What is a metric on a line bundle? What is a line bundle in the first place? It's a holomorphically varying family of one-dimensional vector spaces. What's a metric on a one-dimensional vector space? It's some inner product, but any two metrics are related by multiplication by a positive number. This is an obvious fact from linear algebra, right? So akin to that, if you take any two metrics on a line bundle, they're related by multiplication by a positive function, namely of the form e raised to minus f. So if you change your metric h to h tilde, which is h times e raised to minus f, then the curvature changes, and you can compute this on your own. Theta prime is theta plus del bar f. Now this doesn't appear to be much, but if you take this theta, okay, multiplied by square root of minus 1 over 2 pi. Why am I multiplying by square root of minus 1? The reason is square root of minus 1 times theta is real. Why? Because if I take the complex conjugate, I'll get minus square root of minus 1 theta bar. But what is theta bar? It is del bar ln h, which is minus theta. So it'll be real. Why do I have the 2 pi? That's a more complicated thing. I don't want to get into it. Okay, it's a convention. It has to do with the same reason. That 2 pi is the same 2 pi that appears in the Gauss-Bonnet formula. Integral k dA is 2 pi times the Euler characteristic. So k over 2 pi integral dA is an integer, right? It's for the same reason that there's a 2 pi there that we have a 2 pi here. Alright, so this is a globally defined real 1-1 form. It's obviously D-closed because it's locally D-exact. And its de Rham cohomology class is independent of H. Why? Because when you change your H, your new form is the old one plus D of something, right? So in other words, if you give me any holomorphic line bundle, you can always find a Hermitian metric on it by a partition of unity. So if you give me any holomorphic line bundle, you have a very natural cohomology class associated to it. That's called the first Chern class. How do you compute it? You choose your favorite Hermitian metric, compute its curvature, take square root of minus 1 over 2 pi times the curvature. The cohomology class of that form is the first Chern class. It's a topological invariant, as in if two line bundles are isomorphic, they have the same first Chern class. Right. More generally, if you have a vector bundle and you take trace of theta times square root of minus 1 over 2 pi, that turns out to satisfy the same requirements. That is, it's a globally defined 1-1 form that is closed and whose de Rham cohomology class is independent of H. Okay. That requires proof, and I'll leave that as an exercise. Yeah. So suppose you give me a vector bundle E, you can take its exterior powers. Just like if you take the tangent bundle, you get differential forms, right? 1 forms, 2 forms, 3 forms, so on until the top forms. Just like that, you can take the exterior powers of any vector bundle. So if you give me any vector bundle E, just like if you give me any vector space E, you can take the exterior powers of E. The top exterior power is a one-dimensional vector space, yeah? So if you give me a holomorphic vector bundle, its top exterior power is called the determinant bundle. I mean, in the level of language of transition functions, if you give me transition functions of E, which are basically matrices, the determinants of these matrices are the transition functions of det E. Okay? Then you can easily compute trace of theta as del bar del log det H. Why? Well, what's theta? Theta is del bar of H bar inverse del H bar. What is trace of that? So that's del bar of trace of H bar inverse del H bar. Now this is a standard thing in matrix theory. I mean, if you take A inverse del A, its trace is simply del log determinant A. Okay. So the trace of the curvature is del bar del log det H, but that's precisely the curvature of the induced metric on determinant of E. In other words, C1 of E is the same as C1 of determinant of E. It's not saying much, but it's a useful thing to know later on when we talk about the anti-canonical bundle, etc. Okay, keep this in mind. Alright. Right, so I promised that all of this nonsense is to answer this question, right? How can you come up with a Fibonacci study metric if you didn't already know it? Right? So I claim the answer is the Fibonacci study metric. Once again, I'm only going to talk about its associated 1-1 form. That 1-1 form is simply the curvature of a very natural metric on a very natural line bundle, O1. Okay? So let's try to come up with that. So instead of O1, if you look at O minus 1, there's an O minus 1 is more reasonable to look at, right? It's more obvious to define. O minus 1 has a very obvious metric. Well, what is O minus 1? It's simply a subset of Cpn cross Cn plus 1. And the vector, the one-dimensional vector spaces that that O minus 1 is composed of, they are all vectors in Cn plus 1. And Cn plus 1 is an obvious metric, the one coming from Pythagoras theorem, right? So if you take O minus 1, it has an obvious metric. The key point is, if you compute its first Chern form, sorry, I shouldn't have said the first Chern form. If you compute its curvature, the curvature turns out to be very straightforward. The curvature, I mean, up to a factor, I'm sorry, there are many typos here. The curvature is roughly negative of the Fibonacci study form, okay, up to a factor. As a consequence, if you do the same thing, this metric induces a metric on O1. Well, how exactly? If you give me a one-dimensional vector space and you have a metric on it, that means in a basis it's simply a function. If you give me a one-dimensional vector space and you choose a basis for it, a metric is simply a positive number, right? That tells you how the length of the space is vector. If you take its dual one-dimensional vector space and take the dual basis, then the induced dual metric is simply 1 over h, where h is the metric on the original vector space. Just like that, if h is a metric on O minus 1, locally on O1, the metric is 1 over h. So if you compute the curvature, it's simply going to be negative of the curvature of O minus 1, or in other words, it's just going to be the Fibonacci study metric. Okay, up to a factor. Forget the factor. Okay, so as promised, we know how to come up with a Fibonacci study metric on our own. It's simply the curvature of a very natural metric on a natural line bundle. Okay? So this way of coming up with Kayla metrics motivates us to make the following definition. A line bundle, a holomorphic line bundle, I'm sorry for the typos, a holomorphic line bundle E with a Hermitian metric H is said to be positively curved if square root of minus 1 times theta is a Kayla form. In other words, if this procedure of producing Kayla metrics, taking line bundles and the curvatures of metrics on them, just like for the Fibonacci 2D, works, then such a line bundle is called positively curved. So the O1 line bundle with the obvious metric is positively curved. We have enough language at our disposal now to state the Kodera embedding theorem. It says that a compact manifold is projective if and only if it admits a positively curved holomorphic line bundle. Yeah. So if you take any projective manifold, there's an obvious positively curved holomorphic line bundle, namely the restriction of the O1 line bundle, right? The converse is also true. If you have a positively curved holomorphic line bundle on a compact manifold, that compact manifold is secretly a sub-manifold of projective space. Of course, this only transfers the onus to finding such a positively curved holomorphic line bundle, right? If I give you just a complex manifold, forget about coming up with a positively curved holomorphic line bundle. How do you even come up with one holomorphic line bundle to begin with, right? It's not obvious. So using the Kodera embedding theorem is not a triviality, mind you. Okay. By the way, all of this stuff is there in the book by Griffiths and Harris. Alright, so now we have enough language to at least state one of Calabi's conjectures. So Calabi's volume conjecture is as follows. By the way, I don't know if Calabi actually made this particular conjecture and whether he called it a volume conjecture or not. Long ago, when I took a class with Xu Shong Chen in Stony Brook, he referred to this conjecture as Calabi's volume conjecture. Okay. So given a Kayla class omega, what does that mean? Given a Kayla metric omega such that its de Rham cohomology class is this, and an n positive form eta. What does that mean? You're giving me a top form which is a positive form. What does it mean to be a positive form? That means it's a positive multiple of omega raised to n, where omega is a Kayla class form. Okay. So what you're given is a class and a form. What you're asked to find is a Kayla metric in the class such that its volume form is a given form. That's why it's called the volume conjecture. You're basically giving me a form and asking me whether that form is the volume form of some metric. Not just any old metric, you want it to be a Kayla metric in a given Kayla class. And the conjecture is that there exists a unique Kayla metric satisfying this. Okay. So let's restate it in another way. Every metric in the class omega is of the form omega plus square root of minus 1 del bar phi, thanks to the del bar lemma. What you want is something that some phi that satisfies omega phi raised to n is eta. So you're given one equation and you're asked to find only one unknown quantity phi. Okay, so that's reasonable. At least the number of equations and unknowns matches up. So there's some hope for us to solve this PDE. By the way, if you find one smooth function phi that does the job, turns out it's unique up to a constant. That's not obvious, by the way. But suppose I tell you that Calabi's volume conjecture is true. That is, if there's only one Kayla metric, omega phi, suppose omega plus square root of minus 1 del bar phi is uniquely determined, then phi is uniquely determined up to a constant. What do I mean? If del bar phi 1 is equal to del bar phi 2, then del bar of phi 1 minus phi 2 is 0. So I claim phi 1 is equal to phi 2 plus a constant. Why? I mean, basically I'm saying if del bar phi is 0, then phi is a constant. Why is that so? There are several ways to do it. The fastest way is to multiply by phi and integrate by parts to conclude that minus gradient of phi square is 0, so that means phi is a constant. But anyway, don't worry too much about the PDE aspect. The bottom line is you want to solve this equation, omega plus square root of minus 1 del bar phi raised to n is eta. What does this equation look like locally? Locally, it means the determinant of omega plus del bar phi is given, right? So such equations are called complex Monge-Ampere equations, right? The Monge-Ampere equation is basically the determinant of the Hessian of a function is given to you. Find the function, right? Anyway, so this Calabi conjecture, this particular volume conjecture was solved by Yau along with certain other conjectures of Calabi. Solved, I think, in the 80s or 70s in the affirmative, meaning the Calabi conjecture is true. By now, actually, far more general PDE have been solved. Jazzed up versions of the complex Monge-Ampere equation have been solved. What's the complex Monge-Ampere equation? Roughly, it is the determinant of the Hessian of a function is given to you. You can ask whether the trace, any other symmetric polynomial of that function is given, right? Such things have also been done. You can also ask if you take the Hessian of a function and take the inverse of the matrix that you get, you can ask whether symmetric polynomials of that being given can be solved, right? That has also been done. One of the most famous sub cases of it is the J equation, which was introduced by Donaldson, studied by Chen, Song, Wynkoop, etc. Lots of people. So the bottom line is a lot of PDE theory has been developed since Yau has solved this conjecture. But many techniques are essentially very similar. Okay? There have been technical advances, but yes, Yau's original method was quite ingenious. Okay? And to the subject, Aubin also contributed. I'll come to the Aubin-Yau theorem later on, but as far as I know at least, Yau solved this particular Calabi conjecture in its full generality. Okay. Alright, so we'll stop now. Thank you very much.